Next thing we want to discuss is dynamic programming. I mean, I do know many of you probably have heard of it. Many of you have already used it. You had this in the algorithms and data structure course probably in undergrad. So dynamic programming, given that you have this very nice recursive form in the Bellman equation, is going to help you a lot computing the Bellman, the solution to the Bellman equation. So the key point here, when we know the MDP of the environment, of course we can just do these 3 steps that I told you. You can just solve the optimal equations, and then you find the optimal action values out of the solution, and then finally you find the optimal. But the key point, as you saw in the example, was that solving that system of equations doesn't sound like something simple, right? So you need to just do some tricks. And if you think about the general environment, this is something that you would be happy with, right? So you want one algorithmic solution. So can we just come up with one algorithmic solution for finding the optimal path? As the equation is actually showing a recursive property. So what do I mean by dynamic programming? I do know, as I said, many of you might have seen it before. Just to give you the particular example we have in this, that we need for this Bellman equation. So say this simple, very simple example. So you have, you have this equation, right? This is a fixed-point equation. X equals by fx, right? And you want to solve it. I guess someone wants to get in. Yeah, somebody's looking. Yeah, thanks a lot. So I have this equation, right? And you want to solve it. X equals by fx. You have seen it a lot in your courses. And what is the idea to solve it? Well, there are different approaches, like in the numerical computation courses, where students are supposed to get hard questions. They're going to give like a crazy F for the exam, right? Until you find the solution using an algorithm. So you typically write it down in this form. So you're going to write it down fx minus x. And then you set it equal by 0, then you would say, okay, maybe this is possible to be decomposed into polynomials, or if not, I some zero finding algorithm like Newton-Raphson, and then find the zeros, right? This is the typical case. This is the one which is being used by many solvers. But one more efficient approach numerically is to you can say, okay, let's start from one dummy point x0, right? And if that x0 is the solution, then when I put x0 inside function f, the output should be x0 itself, right? But you do it's x1. What you do next? You take x1, you again put it in f, right? And hopefully the next one is closer, right? So x2 is closer to x1. You keep on doing it, right? Hoping that every time the new x that is computed by f is getting closer to what get into f, right? So if you had, for example, in like old days, the age of ChatGPT, like in my time when we can only take the simple engineering calculator with us in the exam, this was the trick. We could solve numerical problems in the exam. So we define f, we write it down in this form, and then we put x as the input, and we write this function in the calculator that whatever is output, put it back. And then you press this AC as fast as you can to get the, and on the winner, the best mark, and pressing it, and no mistake when entering the function. So you do here, right? You put x, you take it out, you give it back to the function, and you keep on going, right? This is the most basic idea of dynamic programming, right? And you can even do it for more complicated problems. In the algorithm course, as I said, you want to find, for example, length of some cube, write it down in this form, and then you solve it by just to the input. So one key point that you should pay attention here, this f that you have here, should have sure after doing this recursion it's going to converge, right? So for some choices of f, this is not going to converge, okay? So let me show you one example. This is one example, okay? It's equal to minus, right? You multiply both sides with, you just take everything in one side, you just factor it out into polynomial, and you're going to find the solution. What is the solution? Can you tell me? Do you have any clue? Minus 1, right? So if you put x to be minus 1, this is minus 1 over 1. Here is minus 1. Minus 1 equals minus 1. That is the solution, right? But say you don't know the solution. What you can do, you can start by 0, right? You put 0 there. This is going to be minus half, right? Then you get minus half. You put it back in the function, right? It's going to be minus 1 over 2 minus half, right? Minus 1 over 1.5, right? Minus 2/3. And you can keep on doing this, right? As you keep on doing it, you see that when you iterate enough number of times, then you're going to get into minus k over k plus 1, right? Now, if k is very, very large, this is roughly minus the solution that. Cool? Now, here in this particular form that I showed you, if you start from any point, you're going to end with this minus 1. It doesn't matter which point you start with, end up with minus 1. Okay? But, I mean, except x equals minus, definitely. You don't want to have 0 in denominator. But the other case is that I just write down the same equation as above in different form. So this one is the same equation as the last one, right? You see it? So if you look at this guy, I just both sides by 2 plus x. It's going to be x times 2 plus x equals my minus 1, right? And then this is 2x plus x squared equals my minus 1. I want to write it down again in the form of x equal by x equal by f of x. So I'm going to keep x here, and I write this guy down. X equals my minus 1 minus x squared divided by 2, right? This is the same thing, right, as that one. Same equation. I again wrote it down in different form, right? It's again the same recursive form, the same recursive expression, but with different f, right? Now, if you have this one, you can simply see that if you start with 0, again, you are going to converge to minus 1. But if you put diverge, right? Each time that you put it in the function, it gives you larger, right? So this is what I meant by the fact that when you are doing recursion, you need to have your f satisfying a bunch of properties, right? So this is just as a hint that by recursion solve the problem. For the sake of the problem that we have in this chapter, it's enough that you think most of the time you're converging. Okay? Everybody's cool? Okay, so if you're cool, then one thing that you might see is that Bellman equation is eventually the same form, right? It's a recursive form, right? Because you have your value, say this value function v is a set of different values for different states, right? Every value is written in terms of all values, right? Now, if you think of it in a vectorized form, you have the value vector being written as a function of the same vector, right? You have value function equals the expression in terms of the value function, and you want to find optimal value function. Or if you use the basic Bellman equation for one particular policy, you want to find the value of that policy. Now, we can again use the same idea, right? We can get the policy, put it inside, like we can start with a bunch of random values, right? We put it in the equation. This is going to give Bellman equation, right? We get a bunch of values at the output, right? And we keep on trying it till the value is going to converge. Like the values that go inside the Bellman equation are exactly the one coming out of Bellman equation. Everybody's cool? So you get the idea? So it's the same idea. The difference is that instead of having one single variable, you have the value function, the whole value function. And one question, do you see that you can think of value function as a vector? Yes? If you don't see it, that's fine. Just let me know. You don't see it? So what is the value function? Say you have one policy. You have policy pi, right? And I write it down v pi of s, right? What is this guy? The state, right? How many states do you have? N different state, right? So how many values this guy could have? N different values. So you can say that this guy could be value of policy pi as state S1, value of policy pi as state S2, and so on till value of pi as state Sn, right? So I can remove this S here. This is the same thing, right? Right? So you want to find this vector, right? Everybody sees that? Okay, so you want to find this vector. This is the same thing as a function, right? A function, if S is even continuous, is an infinite dimensional vector, right? That's the same thing, right? Okay. Now, when you want to do the dynamic programming here, you typically have two different ways of going. Now, one way is to do policy iteration. So the policy iteration starts from the policy. So you start from a dummy policy. You evaluate this policy using Bellman equation. This is what we call it policy evaluation. So I start with random policy, right? I see how this policy works by just computing its values, right? Once that I see the policy is not doing well, then I do policy improvement. How do I do the policy improvement? Well, maybe you don't have it in mind right now, but just as a bit of a spoil. So you can simply say that, okay, obviously this policy is not doing the actions which are giving me the maximum values, right? So I just change the policy to do those actions, even though I don't know that I have the optimal values yet or not, right? And then once I do it, I'm going to get an improved version of the policy. Again, I evaluate the policy using Bellman. I improve it. I evaluate, I improve it. I keep on improving it. The policy is not getting improved anymore. That guy is the optimal policy, right? This is what you call it the optimal, the iteration. Or you can do value iteration. You would say, I don't want to work with the policy. I start with the Bellman optimality equation, right? And then I keep on doing the programming paradigm, this time using the optimality equations, right? By doing that, you are going to evaluate the optimal value, right? Once you have the optimal value converged, then you put it inside the Bellman equation to find the optimal action, and then you find the optimal policy. Okay? So you can use dynamic programming in both cases. In one of the cases, your variable that you are trying to find is the optimal is the policy. So this is what we call it policy iteration. And in other case, your variable that you're trying to find by dynamic programming is the value function. When you do that, cool? Okay. So now let's try the policy iteration. The steps in details. So the first thing is to just do the policy evaluation. And by policy evaluation, I simply mean that I give you one policy pi, and then I want you to tell me what is the value function. I want you to give me this particular vector, right? That is explaining, telling me at every single state, this particular policy pi is giving me what value, right? Now, if you want to do this policy evaluation, this is, again, a dynamic programming using Bellman equation, right? What you can say, well, I have a bit of simplifications here. I just explained them, but if you don't see it, or if it is too much notation, just skip it. That's okay. It's not going to majorly harm your understanding of the algorithm. The thing is that you might be unclear about what exact term you need to put there, right? But it's okay. You can do it all the time based on the available resources. So one thing that I'm going to do here, I am going to just write down, these are the terms that we already have defined. This is the immediate reward that you get at every single state. And if you have the policy pi, you can simply compute it out of the average immediate reward for the action in this form, right? So this is the average immediate reward for one particular action, and then you average it over the policy that's going to be immediate reward for that state. You can simply write down this guy in this form, right? So you could say, here I have R bar. This is my function with respect to policy pi. This means that I get this term. I multiply with the policy at every single action, and I sum it up, right? This is expectation, right? So this is just the other form of the same term, okay? Here, this next thing is that usually in the Bellman equation, you want to have something like this, right? So this is the expectation of the value in the next state given the current state and the action, right? And if you want to do that, and one other thing is that if you want to get from this guy, which is the next value given this state, so you don't want to take the action into account anymore. Any clue? I don't want you to tell me the exact formula. Just tell me what should be. The next, every single action. Now, if I want the average next value, in so this I, this average value given the current state is going to be written in terms of the other one in this form, right? So it's just the average of that guy with respect to A. So moral of the story, I mean, the reason that is because when you are reading this part, when you want to get the Bellman equation in this compact form, you do it, okay? So I am just now writing down the Bellman equation compactly. So the value of each state is given as the expected immediate reward plus this term, which is the expectation of the next value given state. And if you want to talk about the action value, you should write down exactly the same thing as above. Instead of immediate reward for this state, you have immediate reward for this state in action. And again here, instead of taking the expectation, given only state, you need to put the action. Right? So this is giving you a more compact form. Get back to our interpretation of the Bellman equation. If you have the Bellman equation, how do we interpret that? We interpret that we have n different values. Look at the board. We have n different values. And we don't know them, but we do know n different equations which are relating them to all of these equations, the value equals to something of the other values, right? So you can in that form. So now what you're going to do, you are going to say, okay, I don't know what value of this policy. It doesn't matter. I'm going to randomly just say every value is something, right? So I'm going to say that, I don't know, maybe this value is 1, this is 0, the next one is 1, 1, 0, and 2, something like this, right? I just randomly choose those values. The only thing that I should pay attention to is that, can you tell me what should I make sure when I'm just assigning these initial values? The terminal state, right? What should be the terminal state value? 0. That I know that is 0, right? So if I see any terminal state, I'm going to put it 0. If you don't put it 0, it might be the case that your algorithm is not converging, right? This could be, right? But for the others, it doesn't matter. You just randomly choose some values, right? So these values, I don't know whether this is the value of this policy or not. How can I confirm whether this is the value of this policy or not? I can put it inside the Bellman equation, right? What does the Bellman equation say? So the Bellman equations say that, for instance, well, if you want to know what is the value of one particular state, you can write it down in terms of immediate reward plus that extra expectation, right? And you can always compute that extra expectation given the values that you have considered here, right? Say, for instance, I want to know what is the expected next value, so v pi at the next state, given that I am in one particular state. For example, I'm in state 1. What should I do? I need to write down this expectation, right? Now, these values, these v pi's that I have here, I would replace the values I just assumed here, right? I would replace them with those values, right? And if I do that, I can compute this expectation, right? I can compute some number for this expectation. That is not the exact one. Maybe. That doesn't matter, right? What I'm going to do, I'm going to replace those that I assume for every single state. Term, right? So this term is going to next given the current state that I am in, right? If I want to confirm that the values I initially put for different states are correct, this plus the immediate reward should be exactly the same thing as the value I have for that state S, right? So I'm going to replace it here. So this term is something computed out of the values I had. So all of these values I put initially for my value vector. I put them here, v1 to vn. And then this term plus the immediate reward should be exactly the same thing for that. I had a bit of trouble following what I was doing. Just throw everything away. Just look at it right now, okay? If I consider one set of values here, so this guy is v1, v2, till vn, right? When I put it inside the Bellman equation, this guy, I can compute it out of my policy and the MDP, right? So this is not something important. For this one, I need to know values. Wherever I need the values, I'm going to use those yellow values, right? When I find this term, right, this guy should be exactly giving me Vn, right? The value of this state n, right? For example, if I write it down for the first state, V1, going to sit here. This guy should be this term computed as state 1 plus this expectation when I set the values V1 to Vn, right? This should happen if these values that I have initially started exactly. But if I randomly do initiate these values, do you think that this happens? No. You are going to get a new bunch of values, right? So if you write down this equation, the term that comes out of this expression is not going to throw away. You repeat this, right? Are going to converge to the value of the policy. Yes? If you said, I should double check that. If you said that 0, This is one thing. And I guess if you have, like in some environment, maybe the discount factor might should converge, I think. Like if gamma is less than 1, I guess it always converges. With terminal states being, I guess so, but I check, so I'm not 100% sure. Questions? So did you get the idea how you are evaluating? So I'm giving you the policy. Once I gave you the policy, you want to evaluate this policy. How are you going to do it? You just initiate a bunch of random weights, values. You put it inside the Bellman equation. You're going to get a bunch of values, right? These values, put it, you get a bunch of new values, and you keep on until you get a conversion. Yeah? Usually it's smaller than 1, but like in terminal state, typically if you set it even, it's not going to make any trouble. Like if you have an environment like it's going forever, right? You can't have an episode which is not terminating. Then if you set gamma equal by 1, then you could have the case where this value is not converging, right? It's going to get infinite. So, but if it's smaller than 1, typically it's going to converge, right? So, yeah, that's it. Questions? No question? Okay. So, yeah, if you got no question, then this is going to be the value policy evaluation algorithm. So each time that you put your values inside this, you're going to get a new value, say v bar, and this v bar is not the same thing as vn usually, and then you're going to do. So you're going to say new value function. So you get these new values. You again put them inside Bellman equation. You see what this Bellman equation gives me for every single. Now at the same time, you repeat it, right? Keep on repeating till you converge, right? Okay. Questions? Now, once again, as I told you before, I totally understand if you don't see every single details of derivation. That's totally fine. I hope the big picture is clear for you, what we are doing, right? And whenever you want to use it, of course, you can in detail what number you should exactly put there. You can follow the main picture, right? The main progress, right? Everybody sees what we are doing, right? So please just do not confuse yourself by paying too much attention. Okay, cool. So now we can write down the pseudocode for this policy evaluation. So typically, if you want to do policy evaluation, I'm going to give you a policy, right? And you could start with some initial values, right? So you typically, the initial value is 0 for the terminal states. And for the rest of them, you just randomly choose something. Now, forget about line 3 right now. We don't care about that. What we're going to do, what should I do first? I have the policy, and I initiated a bunch of values. What first? Going to first compute the immediate reward, of course, and then after doing the immediate reward, you can simply put it in the Bellman equation, right? This is immediate reward. You put it here. Then this is the Bellman equation. This is going to be the values that you have. So k first is 0, right? You start with your initial state. Initial value function. and then you compute this guy. This guy, you can compute it. I hope that I could make it clear for you that you can compute it. If not, take it from my side. Trust me, I'm not lying. That line 9, you can compute the right-hand side. And when you compute the right-hand side, you are going to end up with a bunch of new values, right? And call them V1. Started with V0 for each state. No, V1, right? Now, you have this V1. You are going to check whether V1 is exactly like 0, right? How you can check it? Well, you can compute this guy, right? You could say that V1 minus V0 at every single state, I compute the difference, right? And then I take this, I consider the state which has the worst difference between the two values, right? I take that one. This is going to be delta, right? So it's going to explain how different your new value is to the previous value function, right? And now, as long as these two are not the same, so as long as this delta is large, so this is what we're going to do in line 7. So as long as delta is large, so it's more than some small epsilon, we keep on iterating. So you again get V1. You put it again, same. V2 and V1 are the same thing. If they are the same thing, you stop. If not, you keep on going, right? Everybody's cool? Questions? Yes. Policy. You're just initiating your value, right? And then, yes, you initiate anywhere. The only thing that you should pay attention is this one, that the terminal state should have value 0, right? So to divergence. That could happen. Questions? No question? OK, cool. One thing here, line 3 that I told you. So this epsilon is a kind of threshold. You converge exactly to what you want, you get close to it, right? And then you put a threshold, a tiny epsilon. Like as long as what I get is just changing tiny bit in every iteration, I'm pretty sure that I have converged, right? I am very close to the value, right? So you approximate to solve it. And of course, with this delta infinite, is just to start going in the loop, and then it's going to get updated, right? OK. Great. So dummy grid world. I know that everybody laughed when I started with dummy grid world, but I guess now you're appreciating that, right? It helps a lot understand what is going on in algorithms. So if you want to use this recursive form, right, to compute dummy grid world, simply use how we can do it. Say I have given you this policy. So the policy is given. I have told you at every cell what you're going to do, right? Is given, right? Now, the only thing is that you want to find out what are the values. Like if I play with this policy at every single cell, what is the value that I'm going to collect, right? If you want to do that, then, of course, you can, first of all, start by computing the immediate reward in every single state. So the immediate reward at 0 is 0. At 1, obviously, is -1. At 2 is -1. At 3 is -1 again, right? At any other cell that you are, the immediate reward that you're going to get is going to be -1 because you always move to another cell, right? So that's it. That you can write based on the policy and the M, right? Nothing else you needed to compute it, right? You did policy to compute that. That's the first thing. Now, next thing is to compute the second term inside the Bellman equation. I told you you can compute it. I tried to show it in terms of equations. But you can simply see it right now here, right? What you could say that, say I have initiated or I have considered one particular value function, v pi k, in iteration k. So here I have 4 different cases. This means that my value function v pi k, this guy, is going to be v pi k at a state 0, v pi k at a state 1, v pi k at a state 2, and v pi k at a state 3, right? I have 4 different values, right? The first one you always know is 0. I mean, obvious, right? But these 3 guys, say you don't know it and you want to evaluate it, right? So you have this 4-dimensional vector, and you are in one particular iteration k. Now, say that you are in state 0. State 0 is the terminal state, right? Now, what is the value of the next state in average when you play with policy pi? If you play with policy pi, does terminal state, you're going to remain in the terminal state, right? So this bar, this future state, is going to be again 0, right? And then the expectation is going to be the value of that state itself, right? You're in a state, you're in this terminal top left cell, you're going to remain in top cell left no matter what, even if you play with pi, right? And this means that the value that you're going to collect is the value of that cell itself, right? Now let's try another one. Let's say you're in cell 3, below right. When you play with this policy, what's going to be your future state? You're going to be a state 2, right? Now, you are playing with this policy pi. Your future state is definitely 2, right? So when you are in, you play with policy pi, you end up being exactly in a state 2. So this expectation is whatever your value function is at a state 2. Everybody's cool? You see it? Same thing for the other 2, right? You can compute these ones easily. And since you can compute this, you can write it down in the policy evaluation algorithm, right? So you start with a bunch of values. So you initiate a bunch of values. But one thing that you pay attention is that the top left, the cell 0, is a terminal state. So you're going to initiate it by 0, right? But for 1, 3, you can use any value you want. And when you do it, then you're going to get inside the loop, right? So you would say, I go inside the loop. I update my next value at every single cell using the Bellman equation. The Bellman equation, for instance, for the cell number 1 says -1 plus that expectation, which was a value of the previous iteration at cell 0, right? Same thing going to be for line 5 and line 6. So line 4, 5, 6 are eventually the Bellman equation, but Bellman equation both would be the value function. Now I'm treating the left side as the value function of iteration k plus 1, right? The value function of the iteration k, right? And I keep on iterating, right? Till I see no change inside my value function. Now for this one, how many iterations do I need to do? 1, right? So red guy is going to be 0, right? So these are going to be 0. This is going to be exactly -1. For this one, whatever that guy was, in the next iteration, I'm going to give you the right value, right? So you just iteration, right? So larger improvement, you keep on till it converges. Like the values are not changing from k to k plus 1.